Hey everybody. So a few more ideas related to the unit circle. This should be a shorter video, I hope. So here I have a picture of the unit circle. It might be a little bit busy. There are no shortage of versions of this to be found online. It's probably a great idea to construct your own. Um, you know, these are some of the typical values. These are some of the angles that we typically know the values for the sine and cosine function on the unit circle. So just as a reminder, remember the definition we have. If we're given an angle theta, that looks too chunky to me. Let me make it a little smaller. If we're given an angle theta, the cosine of that angle is the x coordinate, where that angle intersects the unit circle when placed in standard position, and the sine of theta is the y coordinate, right? That's our, oops, missing an n up here. So what this unit circle shows us is the values of, shows us various angles, and then the coordinates where that angle would intersect the unit circle when placed in standard position, which of course, based on that definition, gives us the values of sine and cosine for those angles. So let's just take a look at one. I will highlight one here. So if I have an angle at standard position, remember that means it starts, let's make this thicker. It starts on the positive x-axis. So there's one side of the angle. Let's take this angle right here. Okay, so theta, in the case I'm talking about right now, is this angle. So what this unit circle does is shows us, first of all, these two numbers right here are the radian and degree measure, right? So you can see the degree symbol, and then the radians are the ones with the pi's in them. And so based on this unit circle, I can see that the cosine of, I like to do radians, so 2 pi over 3 is equal to, so cosine is the x coordinate, and on the outside of the circle we have the x coordinate. So the cosine of 2 pi over 3 is negative 1/2, not negative 1/3. And the sine of 2 pi over 3 is the square root of 3 over 2. Okay, so that's useful when we happen to be dealing with these particular angles, right? There's an infinite number of angles around the unit circle. So in most applications in real life, these don't happen to be the angles we come along, but these are nice ones to know because lots of things can be approximated by them. They do show up now and again, and they're also just good for getting used to the ideas of sine and cosine. It's also a good idea to familiarize yourself with this circle so that for those of us for whom degrees are more familiar, this will help us start to kind of, like if you live someplace like the States where Fahrenheit is the temperature measure, and you move somewhere with Celsius, it takes you a while to get used to thinking, wait, is 22 degrees Celsius hot or cold or in the middle, or what is that? Same thing here. If you're used to degrees, 60 degrees, 360 degrees all the way around, we want to start getting familiar with radian measure. And so this gives you lots of opportunities to do that, right? 60 degrees is pi over 3. Pi over 4 that we did in the last video is 45 degrees, and so on and so forth, okay? So I just want to make you aware of this and encourage you to start spending some time with it. We will see it over and over in this series of lectures. Another thing to note, let me clean this up. We really only need to look at this first quadrant, or at least that's a good place to start. If you notice, the values that we see here, root 3 over 2, 1/2, root 2 over 2, root 2 over 2, 1/2, root 3 over 2, sorry, I should have started with 1, 0, and then 0, 1. we see similar values on the other, in the other quadrants, right? The differences are the signs. So for example, let's look at pi over 3. This is a nice chance to think about circles, or triangles, excuse me. So imagine, let's see if I can grab just that triangle. I don't know if I can. It wants me to grab the whole thing. In any event, this triangle right here, right? Remember, because of just looking at what these coordinates are, I know that this side is 1/2, and this vertical side is √3/2. This angle pi over 3 right here, it's pretty easy to see that we have the same angle over here, just in the opposite direction, right? That's that reference angles we were talking about. So I could reflect this triangle to the other side, and I have the exact same distance here. This height of √3/2 is exactly the same over here. But notice the distance 1/2 is now in the negative direction. And so this point has coordinates 1/2 √3/2. This one has coordinates -1/2. Same distance, just in the other direction. We're still going in the same direction for y, so that one stays positive, right, in the vertical direction. And so all of these, right, you can play this game with each of these quadrant 1 values to the quadrant 2 values. And then you can do it again. I can get this same triangle again over here. Again, same values. We're going 1/2 units this way, but now we're going down √3/2 units. So we pick up a negative now in the y coordinate. And then we could draw the same triangle over here. Notice our x coordinate has now flipped back to the positive side, but the y coordinate remains negative. And so this kind of exercise you can do with each of the values on this unit circle, so that if you know the values, the values in this first quadrant, you can get the values for the rest of them simply by using understanding the geometry of the situation. Okay, so I'm not going to say much more about the unit circle other than we need to get familiar with it, and we'll use it now and again often throughout this series. Let's do one more idea from this section, something called the Pythagorean identity. Let's see where this comes from. So let me draw a nice unit circle, or at least a reasonable one. All right, so there's my unit circle. Let's get it somewhat centered. So let's, as usual, start with an angle. So here's my terminal, initial side. I get some terminal side here. Well, remember when we think about our sine and cosine, we think about these coordinates of this point, right? So cosine of t is equal to x, sine of t is equal to y, okay? If t is our angle in there, right? But there's another way to think about this. That point, xy, remember, it's the intersection point with the terminal side of the angle and the unit circle. Every point on the unit circle satisfies the equation of the unit circle. It's the equation of the unit circle, x squared plus y squared equals 1. Every point on the unit circle, every xy coordinate pair that's on this, when you substitute in its values for x and y, the sum of their squares is 1, right? If they don't, they're not on the circle. That's what it means to be on the circle. Well, that means cosine of t and sine of t, which are defined as points on this unit circle, must also satisfy this relationship. And so for any given angle, it is always the case that the square of the cosine of the angle plus the square of the sine of the angle is equal to 1, okay? And this is what's known as the Pythagorean identity. You might guess that it's related to Pythagorean formula having to do with triangles, and that there's no accident there. You can draw this triangle and see that x and y are sides of a right triangle, and the sum of the squares of the sides are equal to the square of the hypotenuse of a right triangle, and the hypotenuse is, because its unit circle is 1, right? And any point on this, pick another point on this circle, we can draw another right triangle with a different x and y coordinate, but they still have that same relationship, right? So the equation of circles and the Pythagorean formula, there's a very strong relationship there, also related to the distance formula, which is why this translation from this new perspective from circles as opposed to triangles for trig is less of a surprise than maybe it seems in the beginning, because there is this connection between them, but gives us this nice identity. A quick word about notation. People often write this to mean what I've written up above, okay? So what it means, it's an abusive notation. It shouldn't mean what it's the way it's written. It's a thing that is what am I trying to, convention that everybody uses, but it doesn't really follow the standard rules, but it is what everybody does. So when we write this squared between the cosine and the t, we really mean what I've written here. You're taking cosine first of an angle and then multiplying that number by itself, right? What I've got at the end here, okay? This is going to be particularly frustrating later when we put an exponent in the same spot to mean something different. It is undeniably confusing, and if I could figure out a way to change every textbook publisher in the world and mathematician and scientist's opinion about this, I would, to get a nice consistent notation, but we don't have it, and we just have to get used to that. So for now, this is the meaning of that. Later, we'll see that there's in certain contexts, a different interpretation. More importantly, how is this useful to us? Well, a very quick example to finish up. Suppose I know that the sine of some angle theta is equal to 5/13. Can I find the cosine of that angle? Well, let's try using this identity. So we know that for whatever this angle theta is, cosine squared of that angle plus sine squared of that angle is equal to 1. We now know that cosine squared plus, we know what sine is, so 5/13 squared is equal to 1. With a little bit of algebra, you get that cosine squared theta is going to be, so I'm just subtracting 1 minus 5/13 squared, turns out to be 144 169ths. Okay. So finally, we would take the square root of both sides. Cosine squared theta equals this, take the square root, we get cosine of theta is equal to, well, the square root of this is 12/13, but so is it negative 12/13, right? So there's two possibilities. So as stated, this question doesn't have a unique answer. There are different possible answers, and let's just quickly see why to finish up. So, oops, so maybe I'll just start this over. So let me draw this unit circle again. Oops, why did that not work? There it is. All right, here's my axes. Let's get a circle up there. All right, So when we say that the sine of the angle is 5/13, remember what we mean. We mean that if we draw that angle in, the place where it intersects the unit circle has a y coordinate of 5/13. So 5/13, let's see, this is our unit circle. So this is 0, 1. 5/13 is a little less than half. So half looks to be about there. Let's estimate right here. If I draw this horizontal line at y equals 5/13, it intersects the circle in two places, right? Both of these places have a y coordinate of 5/13. It's getting a little busy. Maybe I'll take this out here, right? So what that means is there's some angle over here. I'll call this θ1. This goes to there. And then there's also an angle over here. Call this θ2. That has the exact same y value, right? There's actually infinite angles. I could keep drawing circles around, angles that go around and around and around and hit that one, but I'm just going to do the two simplest ones for now, right? Both of these angles would have a sine of 5/13. And so the question, when we ask what is cosine, the answer is we don't know. If the original angle was this one over here, we can see the x coordinate must be positive. There's our positive 13. And on this side, it must be negative, right? And so that plus or minus that showed up here is just a reflection of the fact that this question doesn't have a single answer. There are two possibilities. So if I wanted to ask you, if I wanted to re-ask this question in a way that did have a single answer, I would have to say something like, suppose sine of theta is 5/13 and theta is in quadrant 2. What is the cosine of theta? And now we know that it has to be the negative value because quadrant 2 is this quadrant over here, right? 1, 2, 3, and 4. Okay, so that's when we have this square and we take the square root, we get these two answers, and we can do it the other way. I'll leave that to you to do it the other way. If you've given a cosine looking for sine, you'll get answers corresponding to being above or below the x-axis. But in both cases, without that extra information of which coordinate we're in, we have possibilities instead of answers, except for, I guess that'll always be the case. Okay, that's it for this one. Thanks, everybody. I will see you next time.